Okay, so now everyone, we are going to take a close look at what's going on in the ground beneath our feet once again. And we're going to do a couple quick experiments to demonstrate the properties of the material that make up the ground beneath us. The material that stores the water that we're studying.
The regolith.
The regolith, as it is sometimes called, yes. Now, a couple of reminders. Permeability was how easily and quickly the water passes through. So if the permeability is high, the water will pass through very quickly and easily. If the permeability is low, the water will have difficulty passing through. It'll pass through very slowly.
On the other hand, another very important term was the porosity. Okay, the porosity was how much space is found between the particles. Okay, so that's permeability was about the flow. Porosity, on the other hand, was about how much space was between those particles.
And one of the important things about porosity, when you think about it, is porosity is going to ultimately determine how much water the soil can be storing for us. How much water can be stored down there really is related directly to the porosity, because those spaces that are now filled with air will soon be filled with water. More air space will be more water space. Okay, so we'll begin our experiment with the smallest size bead. You all have a copy of this at home, so you can follow along and enter the data that we provide for you, the data you observe. Mr. Livingston, anything?
No, I think that's, just make sure that you follow along with us, because we are going to move not too quick, but quick enough that if you don't pay attention, you're going to struggle. So make sure that you follow along with us and keep up with us.
And hit the pause button as needed. So first, our smallest sized particle. The smallest bead is 4 millimeters. Trial 1, we've already measured the height of the beads. The height of the beads is exactly 34 centimeters high from top to bottom, and they're 4 millimeter beads. So the first thing we're going to figure out is the rate of flow. How much water flows through there, how quickly the water flows through there. The second thing we're going to figure out is how much water is required to fill those pores. Now again, what are those pores presently filled with? And the answer is?
Air.
Air. So that really, number 3, what are we really measuring? Porosity.
Porosity.
Okay, so a simple calculation from 3 will give us 4. Now water recovered is interesting. When we drain the water out, will every single molecule of water exit that tube? No, the answer is no.
Find out, yeah.
All right. Water will continue to cling to these beads. A reminder, what part of the bead will the water cling to? The water is going to be clinging to the surfaces. So I want you to think right now about a little hypothesis. Which one of these will have more water clinging to the beads when all is said and done? Tinier particles or the largest particles? Which one will retain the most water clinging to their beads on their surfaces?
That really, guys, is a really important question in earth science, because if you are studying groundwater, or if you're somebody who works with groundwater, you have to be able to answer that question to find out whether people in a certain area are going to be able to access the groundwater, or will there be enough groundwater. So even though it's just a lab for us right now, that's a really important question.
Outstanding. So, well, let us begin.
Yes, let's go back to our chart.
Okay, the instructions are going to call for us to start with exactly
let's see,
looks like you'll be editing that out, Mr. Livingston.
pour about 20 milliliters of water into the cylinder while your partner clocks. So we're going to add 20 milliliters of water.
But first, we're going to have 300 milliliters of water measured out. So 300 milliliters of water, which we are fairly close to, we're going to have measured out.
Is this also going to need 300?
It is going to need 300. How long the water takes to travel from the top to the bottom. And that, you know, is indirectly going to be measuring our permeability.
above all things, kids, safety first and cleanup first. We should always make sure that we clamp the bottom so that we don't have a spill on our hands.
Okay, looking good.
All right,
Okay, so now I'm gonna throw about 20.
Want to go on the other side?
No, I'm good. About 20 milliliters of water in here. Now, as soon as the water hits the surface, we're going to begin timing. And as soon as it reaches the bottom, we're going to stop timing. Ready, Ms. Livingston?
Mm-hmm. All right, time.
2.97 seconds, correct?
2.97 seconds.
So we had 2.97 seconds. It's going to be our first bit of data.
Make sure you record that number in your chart. So the first thing is 2.97 seconds.
Okay.
Final run.
Now we fill up to see how much it's going to take to fill these pores. Okay. Water is required to fill these pores. All right, so Mr. Livingston, shall we?
We shall.
All right, let's do it. We have a good seal on here now. We will need, at some point, to catch that water beneath. It's always nice to have a little something just in case. And now we are going to put, we're going to stop when we reach the very, very top. How much water is required to fill those pores? That's a little scary.
Still seems to be leaking a bit.
Okay, we'll move quickly.
All right.
Okay. Well, no problem. Now we can begin. All right, so now it's at the top. Let's see how much water was required to fill those pores. All right, try to catch it all. Give it a second. And I think we're there. Okay, so we still have a little coming out, don't we? No, we don't. That's strange. When it's straighter, it's more willing to give us water, isn't it? Oh my God. Yeah, I haven't done that since my years on the farm. Okay.
All right.
Ladies and
Here we
gentlemen, now here we go. Now remember, did we get all that water back? The water required to fill the pores, did we get it all back? Well, no.
Looks like we got approximately, let's see, 100 and that's 100. So we're at about,
Well, actually, just a second, Mr. Livingston. We're a little ahead of ourselves. My apologies. This is my fault. You'll have to edit again, I think. Okay, ladies and gentlemen, we had 300 milliliters of water measured out. We had 300 milliliters of water measured out, and we began to pour. We now have exactly 164 milliliters of water remaining in here. 164 milliliters. So 300 minus 164 is 136. So it took 136 milliliters of water to fill those pores. So 136 milliliters were required to fill those pores. Now, Mr. Livingston, did we get back the entire 136
no,
milliliters?
we absolutely did not. In fact, if I look at this, we got back, let's see, 100, 102, 104, 106. We got about 108 milliliters back.
So we got 108 milliliters back. That means we recovered 108 milliliters. So how much water is still clinging to those particles? 136 minus 108. And the answer is, you do the math in your head, and you get 128. No, you get 28. So the water retained is exactly 28 milliliters. Okay?
All right.
So where are those 28 milliliters? Those 28 milliliters are still clinging to the surface of these particles. Okay? All right. So, let's take a look now at our next tube.
Awesome.
All right.
So now we're going to move to the middle tube. So if the camera can just pan toward this one right here. The height of the column from top to bottom is about the same, 34 centimeters. And the size of the particles in this case is about 11 centimeters. So these were smaller.
Actually, those are the 7 millimeters.
These are I'm sorry, these are the 7 millimeter samples. The 11 are the next setup. So let's do a retraction there. These are 7 millimeters in diameter, and the height of the column is still 34 centimeters.
Okay. So now we're going to figure out how long it takes some of the water to travel through those beads. So the question is, which beads are going to interfere more with the water? Small beads or the larger beads? Which ones are going to interfere more? Well, let's find out. Okay, we have 300 milliliters of water. And we're going to first pour a little bit in and just kind of time it as it travels through. Everyone ready? Everybody ready?
All right.
All right. Here we go.
Okay.
Okay.
So we have 1.87 in this situation.
1.87. Our wetting front travel time,
1.87 seconds.
1.87 seconds. So right away, how does that compare to the time that it took to pass through the smaller beads? Think about that. All right, now let's figure out how much water it takes to fill the spaces in here. So now we continue to add until we have filled it up.
A little bit more.
Okay, I should get some bubbles in here.
We want to make sure that there's entirely water in there, otherwise our result will be skewed.
No bubbles allowed.
All right, there we go.
Okay,
That
just
was-
about there. All right, so now,
Let's calculate the amount of water that we added.
so how much water did we add?
All right, so we had 300 milliliters in a graduated cylinder, just like we had before. In this situation, we have, let's see, 150. Okay, so we have about 155 milliliters left in here. So that would mean that we do 300 minus 155, and we have about 145 milliliters of water added to the column.
Okay,
Now, the percent pore space is going to be how much is released from here. So what we can do is,
that's a calculation.
I'm sorry, not the percent pore space, the
Water recovered.
water recovered, I should say, is, we should probably have a graduated cylinder for that.
Absolutely.
Do we
So,
still need this one?
we will use this one.
I'll let you do that, Mr. Biden. You are a little better at managing the flow of the water out of those things.
Sure, okay. So, well, actually, this is, we're gonna need a bigger graduated cylinder. So, let's see how much water we get back. All right. Okay. What did we get back? We got back exactly 125. 125.
So that means that we must do the amount of water that was required, 145,
high school water recovered, 125.
Oh yes, absolutely, 125. And we're going to subtract 45 minus 125, which is going to give us 20 milliliters. And that's going to be the amount of water retained. 20 milliliters.
Okay.
All right.
Now right away, which held back more water? The smaller beads or the larger beads? Which held more water back? Which still has more water clinging? Smaller beads or larger beads? Well, I'll give you a hint. Whichever one has the most surface area. Okay, and now that takes us to our trial 3, our largest bead yet. Now, time for the largest beads. 300 is not that one, it's that one.
Yes.
Okay, so step 1, I'm sorry, Lauren, can you resume taping?
She is.
Oh, okay. Add that there.
Sorry.
That's okay. No, it's great. You got the little thing that they have in the movies. Take 1. Okay, everybody. Now we're going to take a look at trial 3, which is the largest beads, the largest particles, which are 11 millimeters in diameter. So first, we have the wetting front travel time. Let's see how long it takes. Let's see how long it takes 20 milliliters of this water to travel through these large beads. Are you ready, Mr. Livingston?
Mm-hmm.
Ready? Here we go.
All right.
Okay, that looked pretty quick to me.
Yes, that
Okay.
was 1.37 seconds.
1.37 seconds. That went through pretty quick. Now let's see how much water is required to fill the spaces between these beads. Now notice the spaces are bigger, but there are less of them. Counting on the class to let me know I'm getting close.
All right.
Okay, perfect. Well, I got lucky on that one. Okay, so the amount of water we put in there was, oh my goodness, we put in exactly 150. And from our 300, we lost 150. That means we put in exactly 150 milliliters of water required to fill those pore spaces. 150. Okay, now let's see how much water we recover. How much water do we recover? Okay, from our 150, what are we getting back? Here we go. Notice how quickly it drained?
Just like the waterfront travel time.
Just exactly like the front travel time. Very good connection. Couldn't agree more. Okay. What did we get back? Well, from our 150, we recovered 146.
Okay. I'm gonna fix that. That's not very clear.
Being a left-hander, Mr. Livingston, you are in the way, but you're right.
Yes.
Okay, so the amount of water we retained,
Is 146. If I do 150 minus 146, I get 4 milliliters.
okay, so let's enter that in the bottom one, 4 milliliters. We recovered 4 milliliters worth. Okay, so now we have gathered all of our basic data, and our data is ready for analysis. The instructions to the lab are going to tell us how to figure these out, but we're going to help you out anyway. Now the rate of flow. Rate is in the Earth Science reference table on the cover. So you know that rate is equal to basically the change in value or distance
over time.
over time. Now, step 2, and you always show 3 steps. Our change in value, well, the water went down a full 34 centimeters. And how much time did it take? It took 2.97 seconds.
So if I divide those numbers, I'm going to use a calculator that works here. Calculator that works. I'm going to do 34 divided by 2.9. That calculator is not going to work.
One of these buttons is stuck down. That's the problem. It's got a sticky button.
34 divided by 2.97. That results in 11.45 centimeters per second. So 11.5 centimeters per second.
Okay, now centimeters per second. Now you know that when the unit is given to you in the table, that frees you of the responsibility of having to put it in your box. You can leave it out. So for the remaining 2, we will allow you to do the calculation yourself now that you know how to do it. And you'll show 3 steps. Percent pore space. Percent pore space. Now, again, typically, the way any percent is done, a percent is really the portion divided by the entire thing times 100. A portion divided by the entire thing times 100. We put in 300 milliliters of beads. 300 milliliters of beads. Now, what percentage of that was not beads? Was empty space? 136. That was the amount of water required to fill the spaces between the beads. So there was 136 milliliters of pore space. So let's take a look. Actually, milliliters. So we got 136 milliliters. And to turn it into a percentage, you always multiply by what?
100.
100. And now it's time for a basic calculation.
So 136 divided by 300.
Equals, don't forget to hit equal sign before you multiply by 100. Remember your
That
order
is
of
going to
operations.
give us 45.3%.
Okay, we're going to round to the nearest whole number on this. And we've got 45% pore space.
Mr. Reiner, I think the best way to think about that is your part over total times 100. I think that's kind of the amount of space it took to fill those pores divided by the total amount of, the total volume we use times 100.
Or the part divided by the whole times 100.
It's the same exact logic as saying the amount of questions you got right divided by the total amount of questions that you had on a test times 100. That's how you get your score.
That's how you grade this
Exact same
calculator.
logic.
Okay, so now you know how to find it in each one of these. So you'll be able to find it down here, and you'll be able to find it down there, and then you will have the pleasure of graphing each of these on the graphs that have been provided. And then you can begin to interpret your data and answer some questions. All right, how about throwing some tips their way, Mr. Livingston? Remember, surface area. Where's there more surface area? Is there more surfaces, or are there more surfaces in here? Are there more surfaces in here?
Think about that.
Okay. What do you think?
There are, believe it or not, it may not be necessarily what you think, but there are more surfaces here. Because we have so many more tiny little plastic little balls in there, you have a greater surface area there than you have the larger ones.
Greater total surface.
Greater total surface area,
Exactly.
yes.
Just imagine if we broke these beads into smaller beads to make those. Every time we break one of these beads, we would be exposing a new surface to the world, right? So think of how many more surfaces this has than this, and that's kind of the logic we're using there. And surfaces are what interfere with the flow, and surfaces are what still keep the water clinging to them. So, Mr. Livingston, I think, what do you think? Are we ready to turn the reins over to the kids
I
and let them
think
finish
we're
the
all
work?
set. Thank you for participating in this virtual lab. We'll see you soon.
Okay, remember, show your 3 steps, complete sentences, and turn in a masterpiece that we're going to enjoy grading. Good night.